Okay, so the topic of today, and today is February 20th, which you can see here. Yeah, so is trees. So unlike arrays or linked lists or stacks and queues, which are all linear data types, trees are going to be hierarchical data structures. That's a hard word to pronounce, so they're hierarchies, basically. Hierarchical. What does that mean, hierarchy? Well, that's like ranking as well, in a way, where something comes before something else, and so something is more important than something else, and so on. So at the basic sense, we have the concept of a parent and a child. But before even there, if you remember from linked list, each of the elements of a linked list are called nodes, right? So in a tree, we also identify each element as a node. So here's an example of a binary tree. And it has 3 nodes. Call this node A, node B, and node Z. C, not Z. Node A is considered to be the parent of node B and node C. So parent means it is higher in the hierarchy. On the other hand, node B is the child of node A. And similarly, node C would be the child of node A. We don't really use the term brother or sister or anything like that for like B and C, but we definitely use child and parent. Technically, if node B had a child of its own, then we would say that node B is the parent of node D. And again, we don't really use this notation, but it might appear somewhere. Node D is the grandchild of node A, and node A is the grandparent of node D. So you can think of it like kind of like a family tree in a way, except here it's always going to be single parents. And they can have any number of kids or no kids. So another useful term is the idea of a leaf node. A leaf node is a node that has no kids, basically. What would be an example here of this tree that we're looking at of a leaf node?
D and C.
D and C, that's right. They have no children and therefore are considered to be a leaf node. Or plural, I suppose. Leave. So, why trees? Why are we talking about trees? Well, that's because trees can help you store information that will be naturally in a hierarchy. And the best example for us in CS are file systems on a computer. When you look at folders, maybe Bobby or Sally, you got your home directory, and inside of it, you may have a couple of folders. You may have a folder called CS202. You may have a folder called CS302. And you might have a folder from CS135. Inside of CS2, if you're really organized, you have different numbered folders for each assignment. You might also name them, instead of a number, like, for example, inception assignment or whatever, or string assignment. Same in 302. In 302, you might have a conception assignment, or you might even have in there a subfolder called Star Wars. And in there you have assignments 1, 3, 5, and maybe something else in the future. Okay? And for 135, you probably have a bunch of them as well. This is a hierarchy by nature, right? We basically have the home folder, and that's a parent folder, and then it has child folders, which are 202, 302, 135, and then each of those has its own children, right? This is not a binary tree, though. This is actually going to be some n-nary tree. And whatever the biggest number of child has, so whatever parent here has the most children, so maybe like the most assignment you've ever had was in 202. You had, how many did we have, like 14 assignments, I think? So that would be a 14-nary tree, because that's the parent with the most childs. So we would define it like that. Even though your home directory only has 3 kids, you're still bound by the biggest one. Also, if you think back from like big O notation, and like my example that I gave you when I talked about that, technically I could say that O(n) squared is an element of O(n) cubed asymptotic complexity. Because that's like saying, okay, my sports car runs at 20 miles per hour at least. And even though your sports car can run 100, you can short sell yourself and say it runs up to 20 miles per hour. And you're not lying. I mean, it can go up to 20 miles per hour. It can go higher than that, but you're saying in any case scenario, it can at least do 20, even though it can really do like 80 in any case scenario. Obviously, you don't want to do that. You want to stick to the best case. You want to sell the car. Same thing here. You can say this is a 50 million-nary tree, even though the biggest parent has like 15 kids or something. But still, you could say it's 15 million. But why would you do that, right? So you want to keep it as tight as possible. A special term for the node at the top of the tree or at the beginning of the tree, so the head person in charge or the home directory or whatever is, and it's actually a name that we use in Linux, is your root.
I thought it was going to be C.
C? Well, that's Windows, right? That's your root node.
So up there, node A would be the root node.
That's right. This would indeed be the root node. And in the linked list, this would be like your head. So when you're implementing this, instead of calling it head, you call it a root, but it's generally a pointer. So this isn't actually the first tree that you've seen. You know what this is, right? This is a linked list, right? Yeah. These are all linked lists. But also, you could consider this to be any of these to be a unary tree. It is. It actually is. I mean, like, we don't consider it that, but all this time you have been dealing with trees, just a very special case of a tree, a unary tree. And now we're going to cover the wider range of data structures that include not just unary trees, but binary trees and ternary trees and so on. In this case, because like I said, the n squared belongs to the n cubed, I could also say that this is a binary tree. It's just we never added a second child to any node. In fact, when you have a binary tree that looks like a linked list, we have a special name for it. It's called a degenerate tree. It's actually a really bad thing. Yes, this is an actual term. And so
Is it because it's inefficient?
yes, so that's the next thing that I was going to get to when I talk about sorted. So let's talk about one of the reasons on why we want to use trees, okay? Think back at linked lists that are sorted. What is the access time of finding an element in a sorted linked list? O of n. Because even though it's sorted, worst case scenario is that the number is not found, and it was the biggest number that would have been in the list, because you have to look through the entire thing, right? With an array, you can use the binary search algorithm that I showed you an example with the book, opening the book and splitting it by half, and you can achieve log n time for searching. Well, it turns out with a binary tree, you can also achieve log n, and it's going to be the same sort of system that we were using what we're doing with the tree stuff. And so a binary tree that looks like a linked list because it's going just with one child each is the degenerate tree, and yes, that will basically become log n. So, but let's kind of work our way there. So let's talk about binary search trees. Binary search trees are a special subcategory of binary trees, just like sorted linked lists are a subcategory of linked lists. And so, in our case, how we build a binary tree is we have some value here, so we'll call this value n. And then anything as a left child of n has to be less than that. So less than n, I suppose I should do capital N. And here it would be, or less than or equal to actually. So here, let me just use math. And then here has to be greater than n. So whatever I put there, the dot represents a value that is less than n and a value that is greater than n. And we call this the left child, and we call this the right child. That's the property that's going to make this tree into a binary search tree. And it's going to, in a way, sort the list as you put things in. So, let me give you an example of that using letters. So, we have M. M is considered the root node. And anything to the left of M has to be less than M. The letter F is less than M, and therefore it can be a child of M. On the other side, the letter T is greater than M and can therefore be a right child of T. Okay, let's look at F. On the left side of F, anything less than F can go. So this A here could be anywhere from A to even another F if we have duplicates. What range of letters do you think can go here?
Greater than F to Z.
So you're saying that it has to be greater than F,
Less than n.
Should be less than.
No, it's gotta be less
Less than n.
which have to be less than
Z.
Less than
Or
n.
equal to Z.
M.
Or F.
Not z.
So here's the reason why.
Because we've already split.
You have, when you split something up here, you have to maintain the property of not just this parent, but any parent above it. And so because we split the list with the M as a root node, anything that is less than M can go on this side. So you cannot have a letter greater than M on this side, otherwise it would break the property. Suppose that I pick for there the letter H. What could go here?
G.
B.
G or
Another h.
another H. Yep. Good. What about on the other side? What about here?
I to m.
I to what?
M.
L.
M. which is
What if it's the same letter though? Shouldn't it be greater than equal?
no, don't put great. Don't. You have to make a choice. So when you have equals, you can put them all on the right side or put them all on the left side, but you have to go with one or the other. Otherwise, if you're searching for a letter, then it may lose itself in the process. So pick one or the other. So in this case, we picked the duplicates should go on the left side. We could have also made them all go on the right side, but ideally I'd say stick with the left side and don't mix and match, because remember, you're coding this. You have to write actual code, binary code, that decides whether something goes to the left or the right. So you have to make a decision at that point. You can't just be like, oh, it's okay, it can go either side, right? You can't do that. You have to assert, like, this will go on this side or this side, right? So just pick one side, which in this case we'll pick the left. But still, I'm glad that came up. So anyways, yeah, so I can go I, J, K, L, or M. Okay, I think you guys are getting it. So the T here means that what could go other than P here?
Anything from M to T inclusive?
R, S, and T. Yep, you're right. And then what could go on over here?
Well, Z.
Just Z, basically, yeah. And, well, yeah, I think that's enough examples. Okay, good. So this is what's known as a binary search tree, because now, suppose that I am looking for the letter U. So I'm looking to find U. What I do is, you can think of this like decisions. Each of these nodes are a question that I'm going to ask. So I'm going to hit M, and I'm going to ask a question. Is U greater than M or less than M? In this case, it's greater. So therefore, I have to look on this side to find the letter, assuming it's there. It may or may not be there. Or also, if I'm trying to insert the letter U, okay? So let's go first with the insertion. We got to insert U, so we got to go there. Okay. Is U less than or greater than T? Greater than. So you go there. Okay, you get to Y. Is U greater than Y or less than Y? Less than. So you go here, but there's no child there, right? Well, there you go. There's no child, now there is. And U goes there. So that's how you insert into a binary tree. Okay? Maybe we do one more insert. Let's try to insert B. So we got B. So is B greater than or less than M? Less than M. So now we check F. What about against F? Less than F. What about A? Greater than. So in this case, since there's no child, we just made one, and now it goes there. Suppose that there was a letter before A. Then it would go here, okay? Whatever that was. Yeah, A minus. That's what you're gonna get in this class, right?
A is an A.
That's right, A gets degrees. C's get degrees too. So okay. All right, so now say we're looking for the letter C. Okay, so now we're looking for a letter. Same thing. C is less than M. C is less than F. C is greater than A. C is greater than B. But because B has no child, that is our sign that the letter is not found. So then we can return to the user and say, I'm sorry, C is not found.
Does this mean for all binary trees that the data inside of them reduces to an integer?
It's like sorting, where you have to figure out a compare function. What is less than data? What is greater than data?
Well, yeah, it doesn't.
Which you might want to reduce to some sort of numerical representation, yes.
Okay.
So I would say, yes, you're right.
Is there a way to do it with anything that's not numerical?
It depends on your sort function. Like colors. Suppose you say red is less than green. And that's just a thing. That's a statement.
But even that reduces to an.
You could probably convert that into an enum and then make it into a number. So I guess the answer is probably no. Because you remember, computers are all binary. I can say that all the stuff we're talking about is just 0 and 1, which are numbers, right?
Right.
Otherwise, we wouldn't be able to code it. So I think the answer to your question is yes. We can reduce everything to numbers. But that's a very dangerous yes to say. So
Got it.
get like into quantum computing or something.
So is there like a ternary tree? Or
There's a ternary tree. You could use it for searching. Yeah. Okay, let's try that. Why not? So let's go ahead and insert the letters A, B, C, T, U, V, D. Okay, so we get A. Then B goes on the right side. From there, we go to C, which goes here. Shoot, but what are we doing for the ternary tree stuff here? Okay, I know what we're doing for that. Let's say we have these are both U's, okay? So then we get a T, and then we get a U. So the first U for any U's that are equal, we'll put them down here. And then for D, that's less than T, so that goes here. And then we got another U, so that was going to go right there. And then suppose that we were trying to insert a, shoot. I'm trying to figure out what could make it into a ternary tree here. We got to find something. Okay, let's say let's make this not a T. Let's make it something like a, like an N, okay? Because I'm running out of letters, basically. Okay, now that that's an N, and also let's make this a diagonal. Let's go ahead and insert a O and a P. Okay, so then we're saying O is going to go here, and then P is going to go there, and then let's go ahead and insert a T, or actually a V. So V goes there. So there you go, ternary tree. We could use the ternary branch for the duplicates, the third branch for the duplicates. So there's an example.
third condition would be like,
You have to have a special condition for it. What's that?
So that's basically what I was asking, that your third condition would just be
Equal, yeah. If you want to make it a four-way, you can, but you have to figure out how you're going to decide what goes to which branch, basically.
conditions that are like a range, like you say it's between this and this.
Yeah, you can do that. In fact, that's I don't know if we'll get to that in this class. It's not really part of the class, but they're called B trees. B trees, which is how databases work. They have a range, so each child. See if I remember this correctly. So like this is a node, right? And anything from 0 to 10 will go here. Anything from 10 to 20 goes here. Anything from 20 to 30 goes there. Anything bigger than 40 goes there. Anything less than 0 goes there.
So then you could just have like an N-ary tree.
Yeah. And so B trees basically you do that, and that actually is one of the fastest way to store data. It's like this stuff, but even better, because databases are like when you want to store data and access it quickly. So yeah, so there's definitely a range for that, but you have to define that range. And the way B trees work is they create that for you automatically. So they're really cool. Maybe we'll touch them like last day on study week or something, because they're cool. Otherwise, if you take database course, 456 I think it is. No, that's how I'm talking about that. It's one of those numbers.
Is it 460?
No, that's compilers.
460?
That I have no idea. But it's a number. It's a number there. I recommend you all take SQL. We'll talk about. He teaches it once per year, because then there's a database too. You learn SQL, and you learn relational algebra, tuple calculus, domain calculus, and you talk about B trees for a while. And it's a cool class. I think that's if you want to get a job in CS, the database jobs are like the crappy jobs, but there's always jobs available. So at least you won't starve to death. Let's put it that way. Yeah. Most people, they will work at a database job at some point in their lives, and it's boring. But like I said, it's the most hired area in CS even
Is it
today.
like system administrator kind of thing?
No, it's database administrator.
Oh.
You just basically create queries and manage databases.
Got it.
It's a very boring job, but like I said, it's the most number of CS jobs are database. Like that's the number one job thing. And you don't need that much knowledge, so they're not as well paid, and there's a lot of them, so.
It's.
They're like the kind of jobs you could probably get out of high school even.
It's CS 457.
457, yeah, so. I recommend, in fact, they should make that a requirement course, but I recommend everybody takes it. And Taba's a great instructor. He's, I think, one of the best ones. Oh, that's in video too. Damn, that's like talking crap to the other people, but. I just think that's a really good class. I recommend you take that as your elective. I really, really do, like honestly. If you want to be employable, that is. Okay, back to trees. I was gonna say back to the future for some reason. Okay, so I think we got an idea of what a binary search tree is and how to insert and how to access information. Deleting will work the same way. You basically look for the data. When you find it, you can delete. But then you run into other issues, right? So suppose that I want to delete Y. Okay? So let me just rewrite this tree here. So I want to delete Y. So I'm like, is M greater than Y? Yes. T greater than Y? Yes. Y? Well, Y. Okay. So then you're like, okay, I'm just going to delete that. Well, yeah, but what's going to happen to his children? They're homeless now. They gotta find a new home.
Well, you have to make you the parent.
So in this case, there's an easy solution. You can just have them adopted by their grandfather, basically.
Well, don't you have to put you on the right side, though, to keep it sorted?
That's the next part that I was going to say. The problem with just doing that off the top of the bat like that is that now you have broken the binary search capabilities of this because U is bigger. So then you're like, oh, shoot, well, I can't just do that. So what am I going to do? Well, I can do some rotations. I can basically be like, well, I can make one of the kids become the head of the family, basically, and do that. So an easy solution to, that's actually algorithmically the right thing to do. An easy solution when you delete the parent is to move the left child as the new parent. And then any children that could have. So suppose that you were in this situation here. Oh, there's U here, and then maybe there's a V here. And maybe there could also be something here. Like, well, there was. I never put it. It's a P. And then another U. No, well, we'll change these a little bit just to have variation here. I don't want to use the duplicates. It might confuse you. So here we go. Okay. So this is what we're looking at here. And then all of a sudden, Y gets taken out of the equation. You gotta look at the left child, and that's gonna become the new parent. But then now, who's gonna become the parent of that? Well, the left child again. But then you got X here, right? So you got a problem too. So that doesn't work as easily there. Everybody see that? So the real solution to the algorithm is you gotta find the left child and then the rightmost of that. Because from a traversal point of view, when we talk about traversals, what comes before the Y? X. The rightmost child of the left branch. So of the left branch here, you want to get the rightmost. And now this will actually work whether it's the great-grandchildren. You want to go all the way there. If you want me to kind of prove you that, I can try. Here, I'll just do it like that so I have space. So let's say we have the letter T here. And they have A, C, G, N. And here you could have a B, a D, H, I, J. That's an N? Alphabet failure. another O. Why not? Okay. So as you can see here, if this guy gets taken out, you go to the left side, because here there could be like a, I don't know, something like that, you know? And so if you got to remove the T from this, you go to the left side, and then you go to the rightmost child. So that's R. And that's what you're going to replace it with. No, R goes after that, so otherwise the R would be out of place. Okay, so that's the algorithmic way of doing that. But don't worry, when we talk about implementation of trees then and traversals, it'll make more sense on why. But that's just a quick and easy way of doing that. Okay. So yeah, I'm glad that came up. Okay, so now that you kind of got an idea of trees and binary search trees, let me go ahead and talk to you a little bit about their advantages and disadvantages. So as you can see, trees can provide quicker access and search than a linked list, but slower still than an array. Because with an array, if you know the index location, you can just be there right there and then, right? Here you still gotta traverse things. However, as you'll see, this is log n versus n with a linked list. They also provide moderate insertion deletion time, which is a lot quicker than arrays because, again, you can just put something in the middle. There's no shifting involved. With an array, there would be. And they're slower than unsorted linked lists, because with unsorted linked lists, you can just dump something in the beginning with the head pointer or the end. But they're still going to be faster than sorted linked lists because you don't need to traverse the entire list. You can just work your way down the tree, which, if it's balanced, which we'll talk about later, it'll be faster. It could also be where it's the same in the case of that degenerate tree where it looks like just like a linked list. Because remember, a linked list is a tree. It's just a unary tree in a way. And in that sense, like a linked list, you know, you can just keep inserting things on a linked list until you run out of memory, right? You can't do that with arrays because at some point you got to resize them. Even with vectors, you don't do the resizing, but internally there's resizing happening. So with a tree, you have that advantage that you can just keep creating nodes and appending them, and you'll be good to go until you run out of RAM, basically. So that's a good thing because it's all about pointers, right? They can be kept anywhere in memory. In fact, let's kind of jump a little bit into coding and see the difference between a normal linked list node, which would be something like this, which has your data component and your link component, which sometimes we just call next. And let's see what a binary tree node would look like. It kind of reminds me of a double linked list because you have your data, and then you got your left pointer, and you got a right pointer. So instead of calling it next and previous, you call it left and right. And your right is going to point to the right child, and your left will point to the left child. So this points to another node, which has your data, your right, and your left, and so on. So from an implementation point of view, you'd just be doing something like this. Struct node Yep, be blessed, my child. I don't know. Yep, that's the other thing I was going to say. Here, I can't fit that there, but null PTR. Okay, so yes, this is a binary tree. And I don't want to abbreviate it to B tree because, again, B trees are something completely different. But not completely, but just different. But yes, if you wanted to have a ternary tree, you would have to give it a name, so call it like center child or something, and you would just add it to the list here. In fact, you could just make an array of pointers, which is how you would implement something of n size. You can also do this here. You can make an array of size 2 here.
I can't do this. So it's left equals right equals.
No pointer.
Oh, well, what's the thing about that? Or is that
Well, I was going to put null there, and then I was like, there's no way I can fit that word in there. I mean, I can zoom in and make it really tiny, but
Well, at least the recording captures.
yeah, the recording captures. So this says left, left equals right equals null pointer, which you could do as 2 lines. Left equals null, right equals null. Null pointer is the same thing as null. Just see. Yeah, or actually, you know what I can do to avoid having that? I can use the advantage of C++11 technology. And I can just do this here. Right? That'll compile in C++11, so I'm good. So yeah, there you go. Better solution to the problem. And then I can close my thing. So the reason why I did it this way is because, as you saw, I could have just made data be an actual value, but by making it a pointer, I can be whatever I want it to be and not have any weird issues happening. So if you have an object of some kind, you would just replace the word int by whatever object it is. So if you're using ship names, for example, then it would be system classes star classes store here or whatever. So I'm thinking of doing an ABL tree with the ship thing instead. I don't know. We'll see. I'll have to debate.
Do you ever have a reason to go back up the tree, like, so you have another pointer?
When we talk about traversals, you do. But here's the thing. These pointers are one way, right? So how can we print a linked list backwards if it's a singly linked list? We can use recursion. Yes. Very good. So recursion is what we'll use actually here when we do traversals, because traversals do involve going back up to the tree. So that will we get to probably on the next, after the test probably, because I don't think we'll get to that next class. But yes, that's a good thing to think about, because these are only going in one direction, the pointers. Okay, so back to the usages of linked list. What are the main applications of them? Well, we talked about hierarchy, so manipulating data that's like in a hierarchy, making information easy to search, as we saw with binary search trees, manipulating sorted data in general. So like if I want to just take an entire section of a sorted tree and make it into another list or put it somewhere else, I can take it very easily by just grabbing the T pointer and just pointing it somewhere else, right? So like I can go ahead and be like, just take the subtree here and move it somewhere else, right? I can manipulate that very easily. It's just a single pointer. So that's a big advantage of trees. Just like with linked lists, you can split a linked list into 2 very easily too. You just chop that pointer and make 2 heads. You're good to go. It can be useful when you're trying to, I mean, this is more like a meta, like, you have different layers in Photoshop or something like that. You could think of this as layers in your trees, in the hierarchy of things. Routing algorithms use a lot, and in general, decision trees. So in our case here for binary search trees, our decision was whether something is less than or greater than, right? Another way of putting the decision tree is whether you want to do a move or not. So think about like chess. Each of these nodes is a move, right? And so the child is a potential move that you have. So like in chess, if you're looking at a chessboard, you have, for example, the horse. Do I want to try to draw a horse?
You just use the letter N like they do in
Okay.
The body.
This is the body. What are you talking about?
Why does he have a horn?
It's an ear, man. It's an ear.
Horses have like tiny ears. You don't really
All right, so and suppose that this is where, where can the horse move? The horse can move here, 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 and here. Technically, if there was a spot, it could move here, right? And other places too, like here. But this is like the edge of the board, right? So I think those are the only spots where it can move.
Yeah.
Okay. So you can think of this as a binary tree of the horse. You can think of like the start, which will be your root node. and then it's a 4-way tree. And so this will be like 1, 2, 3, 4. And those are the moves where it can go. So then 1 would be if he goes there.
How ghetto.
It's okay.
This isn't a standard size chessboard.
Well, yeah, it's okay, because here's the thing. If you get to a real chessboard, this tree is going to be insanely huge. And you won't fit it anywhere, not even in a real computer. So there you go. That's the 3 places where you can go, right? So then this has 3 branches. Another 1, 2, and 3. And actually, what we want to call this is we probably want to name all these like A, B, C, D, E, F, G, H. Or you could make it a 2D array. That would have been easier. I, J, but too late now. K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. Oh, wow. We almost ran out of letters there. Okay. So then actually, this would have been D, N, R, and then P. And then these 3 are F, D, E, F, G. So it's G. And then M, or not, is that M? Yeah, that's M and O. Okay? And so you keep doing this, and you build a tree out of this, right? And so now, when you're trying to figure out the win, suppose that the goal of this is obviously checkmate, right? So you need to have a king somewhere, and you're trying to kill the king. So suppose the king is here. And you're trying to find the fastest way to get there. Well, what you're going to do is you're going to build your tree, and the least number of paths to the checkmate point, which is the letter X, which actually would be a child of what is this? R? Or T, that's T, I think. That's M, N, O, P, Q, R. So this guy here has a child, X. And also M has a child of X, technically. So you don't want to, don't do it that way. Just put an X like that. But, so technically that's one way to get a checkmate, I suppose, right? So what you want to do is you want to find the shortest distance from the start to the end. But to do that, you got to generate all possibilities and then see which one's the quickest one. So that's a usage of trees that we'll talk about, and that's more usage of graphs in general. Because this is more of a graph, because really you want those both x's to be pointed to the same spot. So we'll get there when we talk about shortest paths and things like that. But generating the graph in the first place is a tree problem, because it's a decision tree of like, okay, what options do I have from here? I have 4 options. Pick there. Okay, which options do I have from this position? Well, I have 3 options from there, and so on. So you build this big graph, basically.
How's a graph different from a tree?
How's a graph different from a tree? A tree is a subset. So a linked list is a subset of a tree, right? It's a special type of tree. A tree is a subset of a graph. Graph is like the big picture, and then trees is just a piece of that. Trees are technically directed acyclic graphs. But don't worry about that term. We'll talk about that in a month and a half.
The way you have it set up right now, it like, you know how you're jumping from a root to every possible place the knight could go? Wouldn't it be more like you have your root and then you have every other possibility on the board, and then you have to like traverse based on the rules that define a knight?
Yeah, so that would be more like a graph. But I don't want to throw graphs at you because we haven't gotten there yet. So yes, because ideally we just have one letter of each, and then the edges connecting, showing the way, the path. So, yeah, you want as shortest path problem is Dijkstra. We'll come back to this when we talk about Dijkstra. But yeah, so what I'm trying to get to is trees in general and graphs help you solve decision problems. But it's very inefficient because it's going to go really, really fast. So it's going to get like, the possibilities here will be insane. In fact, it's 2 to the power of like 64 or something crazy. So it's really, really big. So anyways, I think I convinced you that trees are actually important in CS and for problem solving in general. So now I'm gonna talk about some of the properties of trees, and let's see how far we get on those. Okay. So first of all, we got. Let me make sure this is still recording. Yeah, we got binary trees, which is a special type of tree that we're gonna talk about for quite a while.
I just noticed you're not recording your voice.
No, that's fine because I'm recording in the video, so
Okay.
the video has the voice. If I try to record voice in both systems, weird things happen.
Oh, okay.
So that's why I'm like ruling one or the other. So yeah. Okay, so binary tree, they have at most 2 children. Otherwise, it wouldn't be binary. They would be ternary or something else. But they can have less than that, as you saw. And again, we typically name them left and right. And in the implementation point of view, whenever a node doesn't have a child or has less than 2 childs, we just set that pointer to null, and that signifies. So for example, O has 1 child with its X, right? So O, internally, on the right pointer, it's pointing to X, but on the left pointer, it's pointing to null, right? And then X has both pointers left and right to null. So implementation-wise, that's what you would do to indicate, and you can check that with an if statement. Okay. So now what I want to do is I want to talk about 5 properties that binary trees have. And the reason I'm going to talk about them is because when we get to some algorithms later on in the semester, these properties will come up. And, you'll be like, well, how do you know this works? Well, because of this property that we talked about. Okay, so first property. We're introducing a couple of terms here. We have the word level. So here, before I even read what this says, let's understand what level even is. So when we have a binary tree, we consider these levels horizontally like this. So we consider this to be level 1, level 2, and level 3. I could technically, although I don't recommend you do, I could draw something like this. However, to avoid confusion, then you would have to put arrows. And so then this would be level 1. And then, in fact, here, level 1. This is level 2, which for this case would be just these 2 nodes. And then level 3 would be these, technically. It's just I drew it sideways. But to avoid confusion, draw your trees like that. Or put arrows. If you're not putting arrows, then you better do them like that. Otherwise, I'll get confused.
Makes it look like a graph.
Yes, which it really is, but we're not getting to that level yet. We'll get there in a month and a half. So, okay, so those are levels. So what this is saying is that if we say levels to signify the keyword, the variable L, we're saying that the maximum number of nodes at a certain level of a binary tree can be represented using the formula 2 to the L minus 1. So I'm saying that at level 3, the maximum number of nodes I can have, as you can see in this case, is 4, right? Could I fit another one in there? No, because now if I fit one more, I have to go either here, 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 or here. And that would be technically, as you said, level 4. Which is, by the way, how many? 1, 2, 3, 4, 5, 6, 7, 8. Leaf nodes. I don't know if I said what leaf nodes are, but it's, yeah, okay, the one where it has no children, basically.
So what if it's an n-nary tree instead of binary? Is it n to the L minus 1?
Yes, very good. Yes, that's right. The base here is going to be the n-nary part. This is binary, so it's to the 2. So I'm glad you made that connection.
Why is it level 8 instead of
Oh, what the hell? I don't know why I wrote 8. I was counting them, that's why. Yeah, I was counting 8. It's because I asked a question as I was writing it. So. Yeah. And so we can check that very fast. So let's see. Level 3 is 2 to the 3 minus 1, which is 2 to the 2, which is 4, and that's right. And then level 4, for example, we can say 2 to the 4 minus 1, which is 2 to the 3rd, which is 8, which is the number that we actually had. So that math formula basically works. So basically, the one thing to make sure this works is you need to consider the root to be level 1. Don't consider that to be level 0. So like, British people, they think of like, base floor and then first floor is level 1,
Yeah.
In America, that's level 2, right? Like you go to the parking lot, then it's, second floor is like literally the one above, right? And yeah, so this is like American style binary trees, I suppose. Do you really believe me that this is the case? Like 100%? I mean, if you don't, I actually have here the proof. Because this can be proven by induction. So let me just write it. It's a good thing to have in case it shows up on a test.
Is that a hint?
I don't know, is it? So for the root, which we are saying is equal to 1, and the number of nodes, which we are saying is 2L minus 1, which is equal to 1, then we can assume, so this is our assumption, that the maximum number of nodes on a level L is 2 to the L, and sorry, I should have written here 1, not that, because I already plugged it in, so yeah. 2 to the L minus 1. So for the root, where L is equal to 1, the number of nodes is 2 to the 1 minus 1, which is 2 to the 0, which is just 1, right? And we can assume that the maximum number of nodes in the level L is 2 to the L minus 1, which is what we're trying to prove, right? Now, since in a binary tree, the maximum number of nodes on the level L is 2 to the L minus 1. Oh, shoot. Right here. I wrote the same thing twice. The maximum number of children is 2. The next level would have what? Twice the amount, right? Which is 2 times our previous thing. And this, of course, can be basically rewritten as adding 1 to that L. So there you go. So let me go over it one more time now that I've written it all. For the root, when L is equal to 1, the number of nodes is 2 to the 1 minus 1, which is just 2 to the 0, which is 1. And if we assume that the maximum number of nodes on the level is 2 to the L minus 1, since in the binary tree the maximum number of children is 2, then we can say that the next level would have 2 times 2 to the L minus 1. Okay? But this, of course, is not in the first test. This is in the second test, by the way. We are at this point we're going into second test material, so not first test. All right. So questions about that?
Will we have to know that proof for the test?
I mean, maybe, maybe not.
Okay.
But you started the proof by assuming what you're trying to prove.
Yes, that's the induction part. That's how proof by induction works. Yes, and your base case is 2 to the 1 minus 1 equals to 1. So the way induction works is you have a base case, you make an assumption and then you basically go to the next term and show that the next term follows your assumption, which
Okay.
follows your base case, which will lead you to the thing. It's
Okay.
it's kind of iffy. If you want, maybe before the next test, we can review induction. But I'll wait, because maybe you might cover it in a different class before then. Okay, so I'm going to move on here, because I want to get through these quicker. Not make that confusing. That, okay? The maximum number of nodes in a binary tree of height h is 2 to the h minus 1. So first of all, to understand what this is, we need to understand what the word height means. This is a little bit different than level. And depending on what book you're reading, sometimes they consider the height to be 0 sometimes for the like one node. So, okay. So first let's start with a single node. The height of a single node is 1. Okay? Kind of like level of a single node is just one level. Again, some books consider that to be 0, but we're going to go with the one case, okay? If that is the case where the height of a single node is 1, then we can say that the maximum number of nodes that can fit in a tree of a certain height can be defined by this function. So suppose that I do height 1. 2 to the 1 minus 1 is equal to 1. And that's true. We can only put one node. Okay, suppose that we have the following tree. That would be height 1, but this will be height 2. So this tree is of height 2, right? So then what's the maximum number of nodes we can have on the height 2 tree? Well, 2 to the squared minus 1, which is 3, as you can see. Okay, what are we at height 3? 7, right? Is that true? Well, let's see. That will be as many nodes as we can fit, and that happens to be 7 nodes. A tree has maximum nodes if all levels have maximum nodes, basically, as you can see here. That's what we consider maximum number of nodes. And so it's basically a geometric series, if you think about it that way. You start out by saying 1 plus 2 plus 4 plus 8, and as you can see, it's a powers of 2 each time, and that's how you get the 2 to the h. And then that minus 1 is because that first part of the geometric series doesn't have 2 in it, it has a 1. So that fixes that little patch. If you wanted to go with the convention where the first node is height is equal to 0, then the equation so this is an aside. This you don't need to know if you do it my way. Then you have to use the equation 2 to the h plus 1 minus 1. And look, that's more stuff to remember than 2 to the h minus 1, right? So I stick with that one. But be aware, you might see the other one.
Is height the same as level?
Depends. In this case, yes. But if you're doing with the height 0 thing, then they're going to be different by 1. So, yeah. But height we consider more in the sense of like when you look at a tree that's not complete and you're trying to see how big it is, you use the term height. Whereas level, we're talking about filling things in. So yeah, essentially it can mean the same thing.
If you put just one node on as the leftmost child and don't complete that level, is it a height of 4?
If you put just one node and don't complete that level, so if you do this.
No, I mean on the previous tree. Or yeah.
Oh yeah.
So
Yeah.
So it's 4?
Yeah.
Okay.
And this is technically the 4th level as well. So yeah.
Oh, okay.
Yep. Okay. And yeah, I'll write this here, I suppose. Height of a tree is the maximum number of nodes on route to leaf path. You always find the path that is longest. So going back to the chess example, we want to minimize that distance, right? However, when trying to store in a computer all the possibilities, we need to consider the height of the tree to figure out how much space we may need for that potentially, right? So use cases of these things is like, okay, if you know that a tree is going to grow up to maybe height 10 or have 10 levels, then you need to be prepared for the worst case, which is where every single level is full, right? They all have nodes in them. So then you can use that 2 to the h minus 1 to figure out how much space you may need in your computer to be able to run this in the worst case when everything is full. So that's a good usage of this to analyze how much requirements you need to run this. So that's just an example. Okay, next one. Oh gosh, we 10 minutes to do them. It just moves. It's messing with me. Does everybody remember ceiling and floor functions? So what does that mean?
Either round up or you round down.
It rounds out his signature.
Yeah, pretty much. So you round up or you round down. That's the easiest way to think about it actually. So if I have 5.6 and 5.6, what is this going to turn into?
6.
And 5.
Okay, cool. So great. That was easy. So what this is saying now, let's go ahead and read it. In a binary tree with n nodes, n being the number of nodes, the minimum possible height or minimum number of levels can be represented by the ceiling function of log n plus 1. Of course, we're CS, where we talk about logs, we do base 2, right? So if I tell you there's a tree that has 10 nodes in it, and maybe we pick a easier number, but no, let's do 10, yeah. Actually, yeah, 10, because of the ceiling thing. So we pick 10. I'm telling you, I have a tree. You don't know what tree I have. I have it hidden somewhere. I tell you it has 10 nodes. What you got to figure out is, in the best case scenario where everything is nice and compact, what's the minimum height that it needs to be? So all you got to do is plug in 10 plus 1 and take the log of that and then take the ceiling function of that. So what's log of 11? I mean, I'm going to tell you that it's something like 3.7 or whatever. I don't know. Somewhere between 3 and 4, okay? Because 4 would be if it was 16, right? And 3 would be if it was 8. So it's in between that range. But either way, it doesn't matter because the ceiling function will make that into a 4, right? So the answer to this is 4. So now I'm claiming to you that the minimum height that your tree can have is 4. It could be bigger than that. It could be a degenerate tree where it's just a linked list, in which case the height would be 10, right? All the way from 1 to 10. But I'm claiming that if you did your job and made it really nice and tight, then it can be at least 4. So let's see. Let's try to draw the best case scenario. How many nodes do we have so far? 7. So we need 3 more nodes. So you can just put them there. And there you go. That's an example of your height of 4. How to screw this up? That way. But then again, we said minimum. We didn't say maximum, right? So, yeah, sure. We're just saying in the best case, you at least need to have those 4 levels. Cool. Okay, last one. Or not last one. Dang, we still need 2 more.
need to recite these rules from memory on the test?
No. But actually, I take that back. In the previous tests, in the previous semesters, I have asked something about this before. Like I've asked the induction thing, but I have asked something like, I have 10 notes. What's the minimum height my tree can be? And then you can just give me the answer. You may not necessarily know the rule, but you could understand how I got the rule, right? If you know the rule, it makes it easier, but you could also just literally try to like draw it out. But I'm not gonna give you an easy number. I'm gonna give you like 250. And then you can draw 250 bubbles, or you can just remember that it's 2 to the h minus 1, right? So that's the kind of questions you'd get.
Would we have to state it, or could we just use it?
Yeah, you can just state it. Yeah, I'll know if it's right or wrong because I'll know the answer. So, yeah. So yeah, because I mean, it's dumb to make memorize things. It's more analyzing things. And if you know the shortcuts like master theorem, then you use them, right? If you don't, then you gotta grind it out. Okay, so number 4, a binary tree with L leaves has at least log L plus 1 levels. And L stands for leaves, okay, in this case. So we're saying if a tree has at least this number of leaves, how many leaves does this tree have here? Not 3, actually. 5. Because all these have no kids. So a binary tree with 5 leaves, we're saying has at least log 5 ceiling plus 1 levels. At least. Well, what's log 5? Again, it's going to be 2 point something, right? Because log of 4 would be 2, and log of 8 would be 3. So this is somewhere in between. But we're taking the ceiling of that, so this is going to give us 3, plus 1 is 4. So we're saying at least it has 4 levels. Is that true? 1, 2, 3, 4 levels. Yep, at least. It could be worse than that. It could be how can I make it? How can I change that? Let's see. I could. I could put that like that. But then I have 4 leaves. Anybody can think of a quick example to show other cases where I have more levels?
You can just make it so that every time it branches, just one of them has the children.
Yeah.
So every level has 1 leaf, at least.
I suppose. And then maybe like, I got 3 right now though. Well, hey, I can just add more. Okay, so 1, 2, 3, 4, and then 5. There we go. There's 5 leaves, but there's more height, okay? Problem solved. That was hard. Okay. Finally, the last one. And I might have to finish explaining that one next time. So just remind me where we left. In binary trees, where every node has 0 or not 2 children, the number of leaf nodes is always more. It's always one more, sorry. Than the nodes with 2 children. So what this is saying is, in a binary tree, where every node has 0 or 2 children, so there's no one child node, so there's nothing like Oh, we don't even have any here, actually. Oh, no, here we have one. This is a one-child node, right? So in the binary tree where that doesn't happen, the number of leaf nodes will always be one more than the nodes with two children. So like, how do we solve that here? We would just throw that in here. And now, we also need one here. So now we have a case where every single node has either no children or two children. And so we have here 1, 2, 3, 4, 5, 6, 7. 7 leaves. And internals we have, or parents, we have 1, 2, 3, 4, 5, 6 with 6 parents with 2 kids. As you can see, this number is one less than that. And that's where that's coming from. I can pick up right here next time, all right? Because it's time to go. Okay, thank you.
Could you go back to that screen real quick?
Well, let me stop the recording real fast.